So, hi, hello everyone. Good evening to all of you. Hi, Pooja. And who's the other one from the name C? So, I don't know. But anyway, yeah. So, good evening and or good afternoon to one and all. So, hope you are all good and safe. How was your Diwali vacation? Have you all enjoyed? So, Samsung Lab 2 is here also. May I know the person who is behind Samsung Lab 2 here? If you don't mind, can you mention your name? Srishant. Okay. 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 Okay, dear. Okay. Okay, let's wait for one more or 1 or 2 more minutes and then we'll start the class. Okay. I hope you all have enjoyed your vacation. Am I right? Or you all have spent your time in preparing for JEE and NEET? Yes. No response. Huh? From class 12. Okay. It's already 4:03. I'll start the class. So we are dealing with coordination compounds lesson. So can anyone tell me the name of the topic? Yes, Pratibha. Good evening. Good evening. Can anyone tell me the name of the topic that we have seen in last class? Till which topic we have covered in coordination compounds in the last class? We have discussed the Bernoulli's theory. Yeah. Hi, dear. May I know your name? May I know your name? Hi. Yeah, Shvikruti. Is that you? Okay, okay. Hi, Shvikruti. How are you? How was your vacation and how are you? Fine. Okay. Okay, okay. Good, good, good. So, students, what is the name of the last? Yeah, I'm fine. I'm fine, Shvikruti. I'm good. Good. So, in the last class, we have discussed about the basic terminologies related to coordination compounds, like what is a central metal atom and what is a ligand, etc., etc. Right? Coordination number, coordination sphere, and coordination entity, and Bernoulli's theory. All those things we have covered in the last class. And in today's class, we are going to discuss the nomenclature of coordination compounds. So, in organic chemistry, we do have some set of rules to name an organic compound using some IUPAC rules, right? The same thing we are going to follow here also. But the rules will be different for both. For coordination compounds, we do have some different set of rules to follow. Got it? So we are going to follow that and name the coordination compound. First, let me tell you that how to write the formula of a mononuclear coordination entity. Mononuclear means only one nucleus containing system. One nucleus in the sense one central atom. One central atom containing coordination entity. And how to write a formula for such system. So the rule number 1 is the central atom is listed first. What you have to do? While writing the name, while writing the formula of a coordination compound, you have to always write the central atom in the coordination entity. That is under the square bracket. Okay, so you can see the iron atom inside the bracket, which is written first, which is central atom. And rule number 2 is the ligands are then listed according to alphabetical order. So in case if you are having more than one ligand in the coordination entity, as you can see in this case, so this is NH3, which is called as amine, and this is chloro. Cl is chloro. So here we are having two ligands. In case of two ligands or more than two ligand containing system, you have to write the ligand according to the alphabetical order in the formula. Okay, while writing the formula. So A comes first, that's why NH3 is written next to the central atom first. Okay. Then rule number 3. Polydentate ligands are also listed alphabetically and their abbreviation or formula should always be enclosed in parenthesis. So in case of polydentate, poly means more than one donor site containing ligands. All bidentate, tridentate, tetradentate, pentadentate, hexadentate, all those are polydentate. So here in this example, ethylene diamine is given. Ethylene diamine is a bidentate ligand, right? So it is a bidentate ligand. So in case if you're having any polydentate ligand, you have to put them in the curved bracket. You should not write the ligand like this. Like chloro, you should not write. Like writing a monodentate ligand, you should not write the ligand as such inside the formula. And rule number 4 is there should be no spaces between the metal and the ligands in the coordination sphere. So here you should not leave spaces. You should not leave spaces. You have to write everything next to each other. This is rule number 4. And the next rule is when counter ion is not written, then the charge should be mentioned outside the bracket as write superscript with the number before the sign. So you can see from this given example. So this is the complete formula, which is a neutral form. And this is the counter cation. This ion is called as counter cation, right? So how many counter cation we are having? We have 4 potassium ions. This is your counter cation. If that ion is not present, then you have to put that charge in the superscript to your anionic system, which is 4 minus. Okay, FeCN6 4 minus. This is rule number 5. And rule number 6 is the charge of the cation should be balanced by the charge of the anions. If you are having 4 cation, then you should have 4 anion. The charge should be balanced. The charge should be balanced. Okay. So you can see the charge of the cation and anion, it should be equal. You should not have 3 plus and 4 minus like that. So both the charges should be same. This is rule number 6 for you. And rule number 7. Yeah, sorry. So students, any doubts so far from the 6 rules for writing the formulas of mononuclear compounds? These are the rules to write the formulas. Okay. So next I'll go with the rules to write the name of a particular compound. Okay. So any doubt? Any doubt so far from the 6 rules for writing the formula of coordination compound? They are very easy. Just very minute thing that you have to be very careful and aware of. So next I'll go with the nomenclature and the rules to write the name for the system which has only one single central atom. Okay. This is very important. This is very important. The cation is named first in both positive and negative charged coordination entity. This is rule number 1. Always, while writing the name, you have to mention the cation first. I'll show you an example. You can see a compound on the screen. So here, potassium is the cation and the coordination entity is the anion. So while writing the name, always start with potassium. Always start with cation, which is potassium. Okay. So this is rule number 1. Then the second rule is ligands are named according to alphabetical order. Ligands are named according to alphabetical order and before the name of the central atom. Before the name of the central atom. Okay. So in the second example, which is here to you, complexes are Cl minus is the anion. That's why they have started with the started naming the compound with the complex. And the example for the second rule is the same compound. As you can see, if we have more than one ligand, yet amine and chloro we are having, no. In this case, you have to follow the alphabetical order. So amine comes first. So how many amines we are having? We have 5 amines. So it is called as penta-amine. While writing amine, you have to write 2M. Don't forget about it. It is penta-amine and it is chlorido cobalt. Chlorido cobalt. This is the cation. And you have to complete that with writing the oxidation state of the central metal atom also. So how to calculate the oxidation number for the system? So let me take this cobalt as X, since I'm going to find out the oxidation state of cobalt. And amine is a neutral ligand. Since amine is a neutral ligand, the charge will be 0. And chloro is -1. Inside the bracket, I have 1 chlorine. And outside the bracket, I have 2 chlorine. I have to include that also. So for that, I'll get -2, which will be equal to 0. So X is equal to +3. So the oxidation state of cobalt is +3. That I have denoted here inside the curved bracket. Okay. Now this is the cationic part. This is your cationic part. And outside the bracket, we have a counter anion, right? That has to be written separately. You have to leave some space between the cation and anion. You can see the space. This is the space. This is the space that they have left between the cation and anion. Okay. Whatever might be the counter ion. Here it can be Cl or Cl2 or Cl3, anything may be there. Since it is present outside the bracket, it has to be written chloride, that's all. Whether it is Cl2, Cl3 or Cl, you have to write chloride. Only if Cl is present inside the bracket, you have to put dichlorido, trichlorido, like that. If it is outside the bracket, you don't have to worry. Got it? This is rule number 2. And coming to rule number 3, the names of the anionic ligands, ending in O, and for neutral and cationic, there are no special suffixes like O. Only if the ligand is anionic, you have to end the name with O. In case of neutral and cationic, you no need to follow some special suffixes like this. Okay. For example, in case of H2O, it is aqua, NH3, it is amine, and for CO, it is carbonyl, and NO, it is nitrosyl. All these are neutral ligands, right? So for all neutral ligands and cationic ligands, you don't have to follow special suffixes. Got it? And there is only one very important neutral ligand, cationic ligand, that is NO+. Okay, that is NO+. That's it. So in case of this particular system, you can see, so H2O is written as hexa aqua copper 2. Here is your rule number 3. And coming to rule number 4. So the prefixes of all monodentate ligands are mono, di, tri, tetra, etc. When name of the ligand already includes some prefix, then what you have to do? Then you have to use bis, tris, tetrakis, pentakis, hexakis, like that. Okay, I'll show you some examples. So this is an example. And here, cyanide is the ligand. Cyanide is a monodentate ligand. It is a monodentate ligand. Okay. So in case of monodentate ligand, you don't have to use bis, tris and all. It is cyanide, so we are using just hexa. Whereas in case of the second compound, here is your triphenyl phosphate. The name of this particular ligand is triphenyl phosphate. So already tri is included in the name of the ligand. So we cannot write by outside this. We cannot represent this 2 as by triphenyl phosphate. Since already tri number is used, the 3 is used here, we have to use bis. We have to use bis to indicate this 2-ppH3 ligand. Okay. So according to the alphabetical order, So chloro comes first and triphenyl comes next. So it is represented as dichlorido bis triphenyl phosphine nickel 2. Okay. And for the next example, you see it is an iron attached with 3 ethylene diamine ligand. So the IUPAC name for ethylene diamine is ethane 1,2 diamine. So already numerals are included. You can see the numbers 1 and 2 here already present inside the ligand. So what you have to do to represent these 3 ligands? You have to use tris. You should not use tri, you have to use tris. Since the name already contains the numbers. So it is tris ethane 1,2 diamine iron. And we have to represent all the polydentate ligands inside the bracket, inside the curved bracket. Okay. This is one more thing you have to note it down. And rule number 5 is the oxidation state of the central atom should be written in Roman numerals in parenthesis. You should not put +2 or +3. You should not put numbers like this. This is wrong. You should always write the oxidation number in Roman numeral inside the curved bracket, that is parenthesis. Okay, potassium hexacyanidoferrate. So how +2 is the oxidation state of this ion? Let me take this ion as X. And since I'm having 4 potassium, the oxidation state of 1 potassium is +1. So it is +4 plus X. And for each cyanide, it is -1, right? So 6 cyanide we are having. So it is -6 equal to 0. And X is 6 minus 4, that will be equal to 2. So +2 is the oxidation state of ion. Okay. Now the rule number 6. If the coordination sphere is cationic, or neutral, then metal atom is written as it is. Otherwise, ATE suffix is added to the metal name. So what I'm trying to say is, if the coordination sphere, if the coordination entity is cationic or neutral, write the metal name as it is. If the coordination sphere is anionic, then you have to use ATE as the suffix. I'll show you an example. So now take this example. Okay, common example I'm taking. So now potassium is the cation and the complex is the coordination sphere is the anion. Now the sphere is anionic. So what I have to do? I have to end the name of the central metal atom with the suffix ATE. I have to end the name with ATE. So that's why it is potassium hexacyanidoferrate. So whereas in case of second example, you can see the coordination entity is neutral. Coordination sphere is neutral. So there is no charge. There is no counter cation or counter anion. So there is no charge, right? So it is neutral. So the thing is neutral. So here you can see we are ending the central metal atom as such. We are not using any special suffixes like ATE. Okay. Nickel means it is nickel. If it is Fe, it is iron. If we are using zinc, it is zinc. Okay. If we are using some copper, Cu, it is copper. And if the central metal atom is Al, it is aluminium. That's all. But if the complex is anionic, then you have to end the name with zincate, cuprate, aluminate, nickelate. Like that we have to do. Got it? So this is dichlorido, triphenyl phosphine, nickel 2. Clear, students? So any doubt so far? For Ag, you can see it is argentate. For Au is gold, right? So it is aurate. And Fe is ferrate. So all these AT suffix we are using if the complex is, if the coordination entity is anionic in nature. Okay. So I'll go with some questions for you. So I hope you have understood all the rules and try to apply the rules that we have discussed so far and try to give me the answer for the questions. So compound A I'll do for you and compound B and C you guys have to try. Okay, and you have to put the answer in the chat box. Okay. Yeah. So write the formula for the following coordination compound. Tetraamine diaqua cobalt 3 chloride. Okay. So what I have to do? Tetraamine. So obviously it is NH3 is the amine and 4 amine we are having. And diaqua. Diaqua. So H2O is aqua and 2 aqua in having. And cobalt is the central atom. Right? So this is the coordination entity and the oxidation state is 3. And outside the bracket we have Cl. Now, how many Cl is present outside the bracket? That has to be determined from the oxidation state that is given in the question. Okay. So oxidation state is 3. Amine is a neutral ligand, so it is 0. Aqua is also a neutral ligand, so it is also 0. Now to find out the oxidation state of cobalt, now to get the oxidation state of cobalt as 3, I have to put 3 Cl outside the bracket. Then only I'll get -3, which will be equal to 0 and X is equal to +3. Okay, got it? So the formula of the compound is CONH3 4 H2O 2 times and Cl3. Got it? Now I want you to give me the answer for compound B and C in the chat box. Can you try for it? Can you try for it? I'll give you some 15 to 20 seconds. Can any one of you or some of you try for it and give the answer? So this is compound number 1. And for compound number 2, compound B. Can anyone give me the answer? It's very easy, right? So I'm waiting for your response. Not even a single student? Okay. Okay, let me do it. It is potassium tetracyanidonicolate. So potassium is the cation and tetracyanido. So Cn is cyanido and it is present 4 times and nickel is the central metal atom. Okay. Now the oxidation status K2. Yeah. Good. What is your name, my dear? It is potassium tetracyanide. Yeah, Shrishant. Okay. So many have joined from Samsung Lab 2. That's why I couldn't identify that it is you. Okay. Shrishant is, that is good. You're good. You have done a great job. The answer is K2NiCN 4 times. So you can see the oxidation state of nickel is 2. Okay. So when do we get 2? When we put only 2 potassium outside, it is +2 + X and -4 will be equal to 0 and X is equal to +2. So there should be 2 potassium outside the bracket as counter cation and the coordination sphere is the anion. So that's why it is entered with the AT. Okay. So this is the formula of the complex. This is the formula of the complex. And coming to the third complex. Can any other try for this third complex? Tris ethane 1,2 diamine chromium 3 chloride. Tris ethane 1,2 diamine. Tris ethane. So ethane 1,2 diamine is this, and we have a 3 ethylene diamine. Chromium is the complex, central metal atom, and we have chloride outside the bracket. You can see the oxidation state of chromium is 3, and ethylene diamine is also a neutral ligand. It is also a neutral ligand. So only if I put 3 chloride outside the coordination entity, I will get the oxidation state of chromium as 3. Okay. So the formula is CrEn 3 times and Cl3. Got it? So now only the charge will get balanced. Clear for all? Clear for all? Shall we move on with the next concept? So try to solve more number of questions from this part. If you get any question from this nomenclature part, you can get you can score marks so easily. Okay, it is not a time-consuming question, so you can get the answer so easily. So try to concentrate on it and solve more number of nomenclature parts. Okay, with more number of compounds. Now, compound is given to you. You have to tell me the IUPAC name for the compound. First, I have given you the name and asked you the formula, right? Now, formula is given to you. You have to give me the IUPAC name of the complex. So, first compound I'll try. From the second compound onwards, you have to try. So, the oxidation state of cobalt is +3. How it is +3? Amine is a neutral ligand, so 0. Cobalt is taken as X and 3 chlorine outside the bracket. So, -3 equal to 0. So, X is equal to +3. Okay, that is a charge. And the name is hexaamine. So, straight away you start with the complex, since the complex is the coordination entity is the cation. So, start with the cation. 6 amine we are having. So, hexaamine, cobalt. Since the coordination entity is a cationic partner, you should not end this cobalt with AT. You have to write the name as such. So, it is hexaamine cobalt 3 chloride. Oxidation state of cobalt is 3, right? So, it is 3 chloride. Okay. So, it is very easy. So, can you give me the name of this compound B? I'll give some 15 to 30 seconds. Try the name for second compound and put it in the chat box. Pentaamine chlorido cobalt 3 chloride. Pentaamine chlorido cobalt 3 chloride. That is correct. Good. Good. Pentaamine chlorido cobalt 3 chloride is the correct answer. Good. So, in the same way, you can try for the third compound also. Who can try for the third compound? Some of you try for third compound. What is the oxidation state of iron in the third compound? Oxidation state of iron. Has anyone got the answer for iron? Oxidation state is +3, right? Yeah, it is potassium hexacyanidoferrate. Very good, very good. Hexacyanidoferrate. Good, good. Oxidation state is +3 and it is potassium hexacyanidoferrate. So it is very easy. It is very, very easy. Ferrate is written because the entity is anionic in nature. So we are ending up the name of the central metal atom with AT. Okay. So now the next topic for today's class is isomerism in coordination compounds. So far we have discussed about the nomenclature of coordination compounds, and now we are moving on with the isomerism in coordination compounds. Okay. So there are two types of isomerism. One is structural and stereoisomerism. We are going to deal with in the isomerism part. So coming to the structural isomerism. So what is meant by structural isomer? They are the compounds with same chemical formula but different bond arrangement around the central atom. Different bond arrangement around the central atom. Okay. They are called as structural isomers. So it is again classified into 4: linkage, coordination, ionization, and solvate isomerism. So these 3 are the 4 classification under structural isomerism for coordination compounds. In organic chemistry also, you might have come across with isomerism in your class 11, right? So there also we had 2 types of isomerism. One is structural and the other one is stereo. But under structural, there were chain isomer, positional isomer, functional isomer, and metamer. But here, all those 4 are different. Here, linkage, coordination, ionization, and solving. Okay. So be careful with this and study. So let's discuss one by one. So the first is linkage isomerism. First structural isomerism is linkage. So this isomerism arises in a coordination compound containing ambidentate ligand. Can anyone tell me the definition for ambidentate ligand? In the last class, I have discussed with you, no? What are ambidentate ligands? Or you give me one example for ambidentate ligand. Can any one of you give me an example for ambidentate ligands? Ambidentate ligand example or the definition of ambidentate? While discussing the terms involved in coordination compounds, I have discussed the ambidentate ligand, right? Under the classification of ligands. Okay, fine. A ligand which is having 2 different donating sites. 2 different donating sites. But at a time, only one can act as a donor site. But there are 2 different donor sites in a ligand. Okay, those ligands are called as ambidentate ligands. The example is thiocyanato. Thiocyanato S and thiocyanato N. So you can see sulfur as well as nitrogen. Both are acting as a donating site. But at one time, only one site can donate. They are ambidentate ligand. So all the ambidentate ligand containing coordination complexes exhibit linkage isomers. Okay. So this Jorgensen has done an experiment and he observed 2 different colors for the compound which is having same molecular formula. Okay. So he was discussing about that, and while doing his discussion, he came to know that it is because of the linkage isomerism existing in it. You can see in the first compound, NO2 is there. NH3 5 times and NO2. This is nitrito N. And here ONO, so it is nitrito O. So nitrito N compound is yellow in color and nitrito O compound is red in color. Okay. So the color difference is because of the linkage of the atom to the central metal atom. Okay. So in the, just a second. So here to this cobalt, 6 coordination sites, donating sites are there. So these 5 are occupied by amine ligand, NH3. So these 5 are NH3 and the 6th site is occupied by NO2. So here NO2. So here nitrogen is bonded with cobalt in case of nitrito N. Whereas in case of nitrito O, cobalt is at the center and now all these 5 sites are occupied by NH3 and the 6th site is occupied by ONO. What is this? ONO. This is ONO. So you can see oxygen is attached with the metal atom. So here CON bond and here COO bond. So that's why 2 different colors are observed because of the linkage, because of the different linked atom. So it is called as linkage isomers. Okay. So NO2, ONO, and SCN, NCS. All these are ambidentate ligands which are having more than one donating site containing system. So they will exhibit linkage isomerism. Linked atom will be different. Now coming to the second isomerism, which is coordination isomerism. So they arises from the interchange of ligands between cationic and anionic entities of different metal ions. So they exist due to interchange of ligand. They exist due to the interchange of ligand. So this is the first coordination compound, and the chromium containing system is the cation and cobalt containing is the anion. So they are one compound. That is one compound. Okay, cation anion compound. So here you can see NH3 is attached with chromium and the cyanide is attached with cobalt. Whereas in its isomer, you can find that NH3 is attached with cobalt and the cyanide is attached with chromium. So what happened here? I have changed the metal ion to make you note down that always cation comes first. Okay. So that's why I have interchanged the metal atoms here. But what is happening? Actually, ligands are getting interchanged. Ligands are getting interchanged between the cationic and anionic system. Okay. NH3 and the cyanide, they exchange their position within the entities to give this coordination isomerism. So simply we can say that coordination isomerism will contain two coordination entity part. Okay, if you find any compounds having two coordination entity part, obviously you can select for the option that the compound is an example for coordination isomerism. Okay, so they exist due to the interchange of ligands. So this is about coordination isomerism. And the third isomerism is ionization isomerism. So when counter ion in a complex is itself a potential ligand and can displace a ligand, which then become a counter ion. I'll give you an example to understand this. So you can see a compound on the screen. Cobalt NH3 5 times, SO4 and Br is outside the bracket. Now this Br which is present outside the entity as a counter anion, they cannot act as a ligand, right? So what it will do, it will try to come inside and displace one of the ligand from the entity. So it becomes like this. So Br comes in and SO4 goes out. Okay. Now SO4 is the counter anion for this particular system after displacement. Okay. Now these two compounds are called as ionization isomers. These two compounds are called as ionization isomers. So when we try to treat this with some other compound, like for example, if I'm treating this first compound with the AgNO3 system, what I will get? I will get AgBr. I will get AgBr as one of the byproduct. AgBr, right? Ag plus and Br minus. So Br minus is coming out as an ion. So when I treat the second compound with the AgNO3, what I will get? I will get AgSO4. I will get AgSO4, right? So here Ag plus and S2 Ag plus and SO4 2 minus will be there. So here SO4 2 minus, sulfate is the ion which is coming out. So different ions I am getting. So that's why it is called as ionization isomers. That's why it is called as ionization isomers, and the phenomenon is called as ionization isomerism. Okay. Hope this is clear to you. Now I'll move on with the fourth isomerism, that is called as solvate isomerism. So when solvent molecule in a complex is itself a potential ligand, a ligand which then become a counter ion, then it is called a solvate isomerism. So mostly water is the solvent. If water is the solvent, then solvate isomerism is called as hydrate isomerism. Okay. Solvent can be anything, but if it is a water, it is hydrate isomerism. So you can see an example. Cr H2O 5 times Cl and 2 Cl is out and 1 H2O is out. And this H2O can act as a potential ligand. So now what it is going to do, it is going to substitute that Cl. So now that Cl comes out, this H2O goes in. So we get 6 H2O inside the bracket and Cl3 is out. Okay. Now Cl3 is the ligand. Okay. Counter ion after displacement. So these two are solvate isomers. These two compounds are solvate isomers. I can write one more isomer for this. Okay. What is that? I can write like Cr. I can take one more H2O out and bring one Cl in. So how does it become? It becomes like H2O 4 times and Cl2 will be there inside and one Cl will be outside and now 2 H2O has gone out. This is also an example for, also one among the pair for this system. Okay, one more is also there. I can take one more H2O out. Cr, H2O, 3 times. Take this Cl also in. So you'll get 3 Cl inside and outside you will have 3 H2O. Okay. This can also be written. So 1, 2, 3 and 4. Now these 4 compounds are exhibiting the solvate isomerism. So number of H2O inside the coordination entity as a ligand differs. Number of H2O inside the entity differs. If it differs, it is called a solvate isomerism or hydrate isomerism. Okay. So any doubt from the isomerism, students? From the structural isomerism? From linkage, coordination, ionization and solvate? I hope everything is clear to you. If you're having any doubt, just put it in the chat box. Okay. Now next I'll go with stereoisomerism. Stereoisomerism means the isomers having same molecular formula but different spatial arrangement of ligands. This is very important. Different spatial arrangement of ligands around the central metal atom. Okay. So it is classified into 2. Like your organic chemistry, it is classified into geometrical and optical. Now coming to geometrical, it arises in octahedral and square planar complexes. It arises in octahedral and square planar complexes. We have 3 complexes: octahedral, tetrahedral and square planar. So these 3 are very common for coordination system, coordination compounds. But among these 3, geometrical exist in octahedral and square planar. So octahedral for octahedral coordination number is 6 and this is the octahedron. Okay. For this type of octahedral system where you have 6 same ligands and 5 similar ligand and 1 different ligand. So these 2 systems will not exhibit geometrical isomerism. Okay, these 2 systems you can see the first system, all 6 ligands are same. And in the second case, 5 are same and 1 is different. So in both the cases, there is no geometrical isomerism present because for a geometrical isomerism to be exhibited by a system should have at least 2 different ligands. System should contain at least 2 different ligands. Then only you can find the geometrical isomerism existing in that compound. Okay, that's why these 2 are not exhibiting. So who exhibit? A system which has ML4Y2 type, they will exhibit the geometrical isomerism. So example is cobalt. Cobalt is a central metal atom and the first type ligand is NH3 and Y ligand is Cl. So it is of ML4 and Y2 type and this is a structure. So you can see the 2 similar ligands are on the opposite side of the central metal atom. If 2 similar ligands are on the opposite side of a system, it is trans. If they are adjacent to each other, it is cis, right? If 2 ligands are on the adjacent position, it is cis. I already told you that this is the octahedral and which is a square planar system. And to this square plane, One ligand is above to it. Okay, one ligand is above, and this is the ligand, and all the ligands which is there on the square plane, they are connected to them. They are all the four which are there on the plane, they are connected. So all the four are adjacent to the ligand which is above. Okay, all the four ligands which are on the plane, they are connected to the ligand which is present above the system. So all are adjacent to each other. So if I am drawing ligands like this, they are adjacent. And if I draw Cl here, then also it is adjacent only. Okay, just by seeing the two-dimensional representation, you should not come to the conclusion that these two are not adjacent to each other. Okay, they are also adjacent to each other only. Okay, if the similar ligands are adjacent to each other, they are cis. If they are opposite to each other, they are trans. So they are geometrical isomers. And this next type, the second type which exhibit this geometrical isomerism is AA2 and Y2 type. What is AA2? AA2 is bidentate ligand. AA means bidentate ligand. Ethylene diamond is given. So here you can see, I'm writing the ethylene diamond like this. Okay, one ethylene diamond, another ethylene diamond like this. And now two chlorine are opposite. So they are trans. If I put it in the adjacent position, it is cis. Okay, this is your cis isomer and that is your trans isomer. So just note the type alone. If they are giving a compound under this type, you can straight away select the options. Okay, you can straight away select that the given complex will exhibit geometrical isomerism because it is falling under this type. Okay. Now the third type is ML3Y3 type. For this particular type, we have geometrical isomerism, but they are not called as cis and trans. For ML3Y3 type, the geometrical isomerism is not called as cis and trans. They are called as FAC and MER. Okay, they are called as FAC and MER. FAC means facial isomer, MER means meridional isomer. Okay, so how to draw the FAC isomer? You can see the picture. So this is your square plane. This is the square plane. And this is one face, right? Left face. And this is the right face. This is the top face. We can put all the 8 faces in the octahedral like this. Now in the picture, in the diagram, which is there on your screen, so you can see that one of the faces occupied by the similar type of ligand. One face is occupied by the similar type of ligand, which is NO2. Obviously, the other face, you can see, the other face would be occupied by the other type of ligand. That is NH3. Okay. So if one face is occupied by the similar type of ligand, it is called as FAC isomer. Okay, if 3 donor atoms occupy the adjacent position, they are FAC isomer. And to write the meridional isomer, what you have to do, in the octahedral, we have a square plane, right? So this is the square plane. These are the ligands which are occupying the corners of the square plane. Now, you take any one of the L shape. Take any one of the L. Okay, take any L. So you can take this L. Okay, you can take this L or this L or this or this. Take any one of the L and occupy that L with the same type of ligand. So here you can see they have took this particular L shape. Which L they have took? They have took this. Okay, the second L they have. You can take any one of the L and occupy those 3 corners with a similar type of ligand. Okay, if it is like that, then the particular compound is called as the meridional isomer. Okay, if 3 donor atoms occupy positions around the meridian of the octahedron, they are called as meridional isomer. Clear for all? So here we are denoting the geometrical isomerism as FAC and MER. And for the other two types, it is represented by cis and trans. Okay, very easy. Don't have to worry about anything. It is very easy. Just see the type. If it is an M, L3, Y3 type, just go for FAC and MER. And you all know, I hope you all know how to draw FAC and MER. Am I right? You all know how to write hereafter, no? Yes. Then coming for square planar. So what I have discussed so far is octahedral. And now we are going with square planar complexes which have coordination number 4. So the square planar complexes also have many types, like we have ML4, ML3Y, and ML2Y2. Like this we are having many, no? So the first two types will not exhibit. Why it will not exhibit? Because all the 4 ligands are same. And here only one ligand is different. For an isomerism, we should have at least 2 different ligands, right? And here only one is different. So the second type will also not give geometrical isomer. But the third type, which is having ML2Y2 type, since it is having 2 different ligands, this particular type will exhibit geometrical isomerism. Okay. So the metal is platinum and one of the ligand is NH3 and the other ligand is chlorine. So this is the square plane and the 2 similar ligands, they are occupying the adjacent position. So it is cis, and if they are on the opposite, they are trans. They are trans. So only ML2Y2 type will exhibit geometrical isomerism for square planar complexes. All other type will not exhibit. Got it, students? So this is your geometrical isomerism under stereoisomerism. So it's already 4:53. Yeah. Shall I complete optical isomerism also today, or shall I continue the optical isomerism in the next class? What do you guys say? Shall I take 2 to 3 more minutes? Say yes or no, at least for this question which I'm asking you. Okay, I'll continue with the optical isomerism. So optical isomerism observed mostly in octahedral complexes. Okay. So as I have told you, geometrical isomerism exists in octahedral as well as square planar. Here optical is mostly observed in octahedral. So there are 2 conditions for a compound to be optically active. First one is the compound should have non-superimposable mirror image and it should have a chiral center. Very, very important condition. Okay. This applies for organic chemistry also. The same condition. If a compound has to be optically active, then it should follow at least any one of these 2 conditions. Non-superimposable mirror image and they should possess a chiral center. What is a chiral center? A center which has 4 different atoms or groups attached to it. That is called as a chiral center. Okay. So you can see. So there is a metal and AA 3 times. Okay. So this type of system will exhibit optical isomerism. It is an octahedral system. Since it is a bidentate ligand, the coordination number will be 2 for 1 ligand. And we have 3 ligands. So it is 3 into 2, 6. So coordination number is 6. So it is an octahedral. You can see the cobalt tris ethylene diamine complex. So this is the first complex. And I'm taking the mirror image of it and I'm getting this. And if I try to place this compound above this first compound, it will not get superimposed, right? They are non-superimposable because to this side, this ligand, this will come and occupy this position. No. So in the same way, the other ethylene diamine which is here, it will come and occupy this position. Same way here also. Now they are not superimposable. They are non-superimposable mirror image relationship containing compounds. That's why they are optically active. They are optically active. Okay. And the second type is AA2, MAA2, Y2 type of ligand. So we have seen the example for geometrical isomerism also for the same type. So there we had cis and trans. Among cis and trans, only cis is optically active. Trans is optically inactive. Okay, you can see cis is optically active because on taking the mirror image and trying to place the mirror image compound on this original compound, so the chlorine, the second chlorine will be placed on, above the ethylene diamond, right? So it is non-superimposable. So cis compound is, this is cis compound, it is optically active. But for trans, we can see two chlorine ligands in the opposite side. They will be in the opposite side. If I take the mirror image, I'll get the same compound. And if I try to superimpose over the original compound, it will get superimposed. I cannot able to differentiate the two compounds. So it will just superimpose on it. So it will not exhibit optical isomer as it is having superimposable mirror image relationship. Okay. Compound has to be optically active. It should have non-superimposable mirror image relationship. Okay. So this is the criteria. And today we have discussed the 4 types under structural, which are linkage, coordination, ionization, Solvay, and 2 types under stereo, which are geometrical and optical. The next class, I will show you, I will give you some questions like this to you in the next class. And then I will start valence bond theory. Okay. Okay, students, you can take down the questions, I think. You just take these 2 questions and you try to draw the geometrical and optical isomers for these 2 complexes. Just take the question alone and do it as a homework. Okay. Take these 2 compounds, take a screenshot or note it down and do it as a homework. So in the next class, we can discuss the valence bond theory. So go through this isomerism and nomenclature part today. And if you are having any doubt in it, you can ask me. Feel free to ask the doubts in the class. Okay. Don't hesitate to ask doubts. Clear, students? Okay, then. Thank you so much for listening to today's chemistry class. Thank you so much. Bye-bye. Take care.